Excuse me. Okay, last class period, we ended with the introduction of the infinite square well. And so now we're going to work on the solution to the Schrodinger equation that matches this infinite square well. So I'm going to erase this lower part because that has to do with the solution that we're going to find. Okay, I thought I erased it. Delete. There we go. And so we're going to use this function. So the blue function here, the potential, is the infinite square well, or the particle in a box potential function. And so this is where we see how the Schrodinger equation is actually used, right? We've done math with it, but we haven't seen how it's actually used. So we start by saying, okay, we have three regions. I'll call them Roman numeral, okay, I'll put it on the pin. Roman numeral 1, Roman numeral 2, and Roman numeral 3. And so we're going to look at our solution that we find in each of those regions. And I think I told you before, Roman numeral 1, Roman numeral 3, it's going to be 0. But we're going to actually look at what the equations would say. So in region 1, excuse me, we have, using the time-independent Schrodinger equation, I don't need a partial anymore because it's only one variable. So I have that equation. Now I have that equation in all three regimes because that is the Schrodinger equation. So I'm going to take this, and before I actually do any calculation, I'm going to just rearrange it. So I have it in the form of d second psi dx squared equals, and then just solve it for what that equals. And so I'm going to have to first, I'm going to move this v over here, and then I'm going to multiply by 2m, divide by h bar squared, and multiply by minus 1. So I've said all of the words. So I'm going to have 2m over h bar squared. I said squared, but it didn't get written. And then, and it does, I do have to think this through to make sure I did it right. It's going to be v minus e. And we cannot forget the psi. So this is our time-independent Schrodinger equation. Just solve for d second psi dx squared. Any questions about the math going from just here to here? It's pretty obvious. Okay, just have to make sure. So now we can apply region 1. So for region 1, d second psi dx squared equals 2m over h bar squared. Infinity minus e, since e is finite, is just infinity psi. Well, that doesn't really make sense, does it? Your second derivative is infinite in the entire range. That's not going to make sense. It can only be true if this here is 0. It's the only way we can make this statement true. And of course, this was region 1 and region 3, because you notice I didn't even put the boundaries yet. I just had the potential energy. I put a number of pages in here. I was going to do that before class, and well, hopefully I didn't, because if I did, now I'll just have a whole lot more pages. So we have psi Roman numeral 1 equals 0, and psi Roman numeral 3 is equal to 0. So now we just have Roman numeral 2 to worry about. If only life was always this simple. So in region 2, so for that same second order linear differential equation, I'm going to find the solution. Now, if you've had differential equations, which none of you have, right? Then you might have a way of solving this. Without having differential equations, I tell you what the form of the solution is, and then we work backward. So in this problem, we are given that v is 0. So it's equal to minus 2m over h bar squared e psi. The solution to this has the form e to the bx. So if psi is equal to e to the bx, now notice I didn't even put a normalization constant. We'll get to that later. What we do now is we plug that in and see what b is going to have to be. So if I plug that in, what's the first thing I should do?
Solve for b.
Well,
Where are we plugging it in?
I'm going to plug the psi is equal to e to the bx into the equation that's, well, combination of orange and red now, and solve for b. So what's the first thing I should do for that process?
Oh, you separate it out into like
Size and accents on the other side.
Well, that's what we would try to do if we were going to try to solve a differential
So
equation.
you're already
But we can't do that. We don't have the math tool. That is, without differential equations, we don't have math tools. And so we just know that psi has this. So what we need to do is to plug it into that equation and see what drops out. So the first thing that I think we should do is take the second derivative.
Yeah.
So this is a hard derivative. What's the first derivative of psi?
b e to the bx.
Yeah, b psi.
Yeah, b squared.
What's the second derivative of psi?
B squared. Psi.
B squared psi. So that part's easy. So let's put that in. So we have b squared psi is equal to minus 2m over h bar squared e psi. Now I'm going to do things, well, as you say, now I'm going to do things right. I'm going to move this over here. So I have b squared psi plus 2m over h bar squared e psi equals 0 equals b squared plus 2m over h bar squared e psi. The reason this is good math as opposed to the somewhat sketchy math we did to separate the time part from the positional part, the spatial part, this is good math because I don't have any division by zero possibilities. This equation can be true either if the thing in parentheses is 0 or if psi is always 0. Well, psi always 0 is what we call the trivial solution. We throw that one out immediately. We say that's not a real solution. If psi is 0, what do I get for the sum of psi mod squared over all space? 0. Well, that's simply not going to be the correct answer. We need to get 1. So we throw that one out, and what we're left with then is the mathematical solution for b. So help me out. What do I get for b from this?
equals square root of -2 over h bar.
There is only one quibble I would have with your answer. And it's an important one in quantum mechanics. Anytime you do a square root, you have two answers. You have to have the plus and the minus, because both of them are solutions. And we're just looking for what's the solution. If there's two solutions, they're both solutions. And now we look at this and we say, well, goodness, if I was in grade school and my teacher gave me this, I would throw my hands up and say, this is impossible. Because I have a square root of a negative value, right? The mass of the particle is always going to be positive. Planck's constant is a positive number. And I didn't specify this, I should have. The energy is greater than 0. If the energy was less than 0, that would be a different situation. But the energy is greater than 0. So if everything in here is positive and we have a minus sign, what do we do mathematically now that we're no longer in grade school? We use I. Square root of -1 is I. So this is equal to plus or minus I square root of 2me over h bar squared. Now let's make life simpler for ourselves, and let's call this right here K. It just makes life easier, right? A lot less to write. So we're going to have B is equal to plus or minus IK. What does it mean now? We did some math. We found the value for B. So let's put that back in. I said the solution was equal to e to the bx. So now we have two solutions. Psi plus equals e to the plus ikx. And psi minus is equal to e to the minus ikx. So we have two different solutions that work. And so just like before when I was talking about, the last class period, psi is equal to the sum of all of these different solutions. Our solution here is just going to be a linear combination of psi plus and psi minus. And how much is psi plus and how much is psi minus depends on how I set up the system. So my full-on solution is going to have to be my full psi as a function of x is equal to a e to the ikx plus b e to the minus ikx. That's my solution. It's a perfect solution. I could keep my solution like that and go to the next step of normalizing, but I won't. I won't because, actually the next step is not normalizing. I won't because there's an easier way to deal with it. So this is where we use Euler's relation. I believe I talked about Euler's relation, haven't I? So do you remember what it is, or just the words?
Oh, it means that the positive part becomes sine kx and the negative part becomes cosine kx.
Okay, so Euler's relation is e to the I theta is equal to cosine theta plus I sine theta. So that allows us to say that A kx plus B e to the minus I k is equal to A cosine of kx plus AI sine of kx plus B cosine of minus kx plus BI sine of minus kx. And most reasonable people at this point say, wow, congratulations, you just went from 2 terms to 4 terms. But now it's explicit in what's real and what's imaginary, at least. Well, it's simpler than that. Because you have learned somewhere in your life that cosine is an even function. It's symmetric about 0. So cosine of minus kx is identically cosine of plus kx. So that's not a good color. So I'm going to change that to a plus sign, and it makes no difference. And sine of kx is an odd function. It means sine of minus kx is minus sine of plus kx. So for the sine one, I have to do two things. I have to put a minus sign here and change that to a plus. So I use the fact that cosine is an even function, sine is an odd function, so that now I can combine these, and I have this is equal to a plus b cosine of kx plus I times a minus b sine of kx. Now, nobody ever said that these constants a and b had to be real. They can be complex. So this here, a plus b and a minus b. I think I'm going to have this actually in a homework problem. I will open up the next homework assignment. It's going to be due a week from today rather than today. So something that we often have in homework that I think I might have put in homework is, well, let a equal a1 plus ia2, right? That's giving it its complex values. And likewise, b will be b1 plus ib2. So we have 4 real constants with our 2 complex constants, is what I'm saying. So the lowercase numbers are real constants, whereas the capitals are complex constants.
So you're able to just make a linear combination of real and...
If something's complex, you can always do that, yeah. There's always the real part plus the imaginary part.
So that thing that you wrote there is just a rule that you can use for separating complex value into its 2 parts?
Well, keep in mind, I'm not separating a function into its real and imaginary parts. I'm saying a complex number can be written as the real part plus I times the imaginary part.
Okay.
So it's more definitional of what complex means. So if I substitute those in, then I'm going to have psi is equal to a1 plus ia2 plus b1 plus ib2 cosine kx plus, and I'm going to bring the i's inside, so it's going to be ia1 minus a2 minus ib2 plus, b1. Here we have space. And so if we look at this, what I have here, it's actually, there's usually another step to what we would do. We want to make these so they're both real numbers. And these can be both real if a2 is minus b2, and this is real if a1 equals a b1. So that's something that we often show, that if we have, if they need to be real, then we can have them both real with this relationship, which you notice that means that A is, or B is the complex conjugate of A for it to be real, for them to both be real. But that was not a requirement. That was just a deviation, just something that struck me as I was going along. So I'm going to come back to here and say, there's nothing sacred about A plus B and A minus B. It's just constant 1 plus constant 2 and constant 1 minus constant 2. And so the difference in a constant or the sum of a constant, those are just two new constants. So to make our lives simple, we're just going to call this C cosine of kx plus, and take the I as well, call that D sine of kx. So C and D are once again complex constants. And now I have it back to the simplicity of what I had before with the exponentials, except for I have sine and cosine, which are often easier for us to deal with. I have a whole lot more feeling for sine and cosine than I do for I kx, e to the I kx plus e to the minus I kx. So that's why we want to do this. So there will be some times in your solutions where you will shift it to sinusoids. There will be other times where you leave it in the exponential. Usually, if it's imaginary like this, you'll shift it to a sinusoid. But there are a few cases where you won't. So the choice is always based on what's going to be easiest. We're not gluttons for punishment just because we're doing some hard math. So now let's get to what we have. We have psi of x. And I better put the region 2, because this is only the region 2 solution, is equal to c cosine of kx plus d sine of kx. So we have this solution, and now we go for the next step. And the next step is not normalization. Remember earlier I said we go straight to normalization, and I corrected myself. No, that's not the next step. The next step is a super important one. It's the one where quantum physics becomes quantized. And that's boundary conditions. Boundary conditions are what happens at the edge of my boundary. Region 2 does not go on forever, right? It starts at 0 and ends at L. And so the boundary conditions are what has to happen to my wave function there. And we have two rules, although one of them has a gotcha. Rule number 1. Psi is continuous. Our wave function cannot have a discontinuous break. That means you can't have the wave function going like this. That doesn't work because that would have a discontinuity. So there's condition number 1. Condition number 2, I swear I did. And later on, we will justify this unless. Right now, I'm giving it to you as a rule. And then later, we will actually show using the Schrodinger equation why it's a rule and why there is the unless. So d psi dx is continuous unless v goes to infinity at the boundary. So you know what? In this case, we're the unless. Most cases, real cases don't have this. Now, I say real cases don't have this. The particle in the box is very close to a real case. Our understanding of how radioactive decay works. We have the potential energy in the nucleus has, some potential energy that's pretty uniform throughout the nucleus. And then when you get to the edge, it jumps way up. It's not an infinite wall. It's a finite wall. So that makes a difference, finite versus infinite. And then it drops away as you go farther away. So a particle in the nucleus for radioactive decay calculations is treated like a particle in the box, except for it's not an infinite boundary. So it doesn't have the unless part here. The reason, okay, so we're not even going to get to this boundary condition number 2 because we have a different situation. Because v goes to infinity, what did that make the wave function outside? 0. And so that replaces this one in our work. So let's do this. Boundary condition number 1, the only one we're going to apply today. At boundary 1, that is x equals 0. I'm going to have psi in region 1 of 0. I'll put x equals 0 so it's really clear. Must be equal to psi in region 2 of x equals 0. Right? That's what the boundary condition of continuity means. The psi has to be the same value on both sides. Well, what was psi in region 1 for all positions? I'll go 0, right. I guess I got to go back too. Yeah, psi in region 1 was 0 for all positions. So that means evaluating this boundary condition, I have 0 is equal to c cosine of 0 plus d sine of 0. Okay, one of those is 0 and one of them isn't. Which one is 0? Sine 0 or cosine 0? Cosine 0 is 1. Sine 0 is 0. It's okay. So this is equal to c. So we have 0 equals c. It doesn't take much math acumen to say, oh, we have just discovered something that makes our wave function simpler. We now have a wave function of psi in region 2 of x is equal to d sine of kx. Right? The c completely disappeared because it's equal to 0 because of the boundary condition. So life's easier, right? We still don't have quantized anything. This is quantum physics. We got to get to the next step to get quantized. So this was the first boundary. Where's the second boundary? X equals? Okay, A or L, depending on which picture you're looking at. Which picture did I use here? L. L for this picture. So I'm going to have psi in region 2 at x equals L equals psi in region 3 for x equals L. So I'm going to have d sine of k, and now x is L, so it's KL, equals, wow, I don't know what's going on, 0. I think my hand's messing things up or something. You see weird things are happening, like it's putting dots on the screen in random places when I'm trying to draw up here. Okay. If d is 0, this is going to be true, right? But what's the downside of that?
That makes the wave function 0.
Yeah, that gives it the trivial solution, so that's not allowed. So what's the other condition? KL is equal to an integral I. But I have to make one caveat there.
Not really 0.
Right. Not really 0. Why not 0?
That would
It again give you the trivial solution. Right. We love trivial solutions, but they're not our answers. Okay, so this is the quantization. Now k can only be certain values. So let's just solve this for k. We have k is equal to n pi over L. That should remind you of something on your test. On your test, you had n equal to 4. I gave you the n equals 4 solution to this problem. Obviously, you weren't going through this work to get there. If you were going to this work to get there, that would not have been a fair question. But now we have k equals n pi over L. And one says, huzzah, hooray, I've quantized something. What have I quantized? Well, it's actually a meaningful observable that I've quantized, but it's not seen in this equation. The book says what? Energy. According to the book, that's energy. That's right, because we define to make our lives easy that k is the square root of 2m e over h bar squared. So this is equal to 2me, and I'll put a subscript of n on that e now because there's going to be a different e for every value of n. I see it's putting over h bar squared. So I'm going to solve that for e, and I get e is equal to n pi h bar squared over 2ml. And I'm going to put it like that. Just so it's clear, everything in parentheses is a constant. M is the mass of my particle, L is the width of my box, and N is an integer.
Didn't we say that k was equal to square root though of 2m?
We did. And so that should have been, yep. I was thinking there was something missing. Square and square and square. Wow, thank you. That kind of thing is embarrassing. So there I rewrote the important part, and hopefully everything I did was right. Yeah.
Shouldn't it just be h bar, not h bar squared?
No, because it was h bar squared in the square root. When we square, it got rid of the square root sign, but it stays h bar squared, just like the 2 stayed 2.
Oh, okay.
Okay, yeah. This the only thing different is sometimes you see an 8 there where the 2 is, and that's because sometimes they'll have half the width instead of the full width, right? So if you had like a box that goes from minus a to plus a, the full width is 2a, and of course 2 squared is 4, 4 times 2 is 8. So that's sometimes you see it differently. But it's a different parameter, so it's the same total outcome. So here, now we have the glory of, ta-da! Only certain energies are possible if the particle's in the box. And now we go to reality, and we say, what does that mean? If I have a box, and I would have the same type of quantization if I had a finite box. If I have a box, and I put this ball in there, according to this equation in the box, that particle cannot have 0 energy. If n was 0, it would have 0 energy, but if n was 0, we'd have a trivial solution, and we'd have no particle in the box. So n has to be at least 1, which means that particle has to have energy. Has no potential energy, so what kind of energy does it have? Kinetic. So you look at that particle and you say, does it have kinetic energy? Yeah, as far as I can tell, no. And so this is where you have to start taking, okay, so what does this mean? This calculation says that I can't have that particle in the box and have it stationary. It has to be moving. Does this defy then quantum mechanics? Does this say quantum mechanics is just wrong? I know the trivial answer is yes. But no, it doesn't, because otherwise we wouldn't waste all our time taking a class in it. This is not stationary.
So it's just like because the particles in the circle, or why can't I think of the name of the ball? They're just spread out.
Well, let's do this. Let's do the calculation and see how much kinetic energy this thing needs to have and how fast it needs to be moving. So for some reason, I have moved all of my meter sticks over to this side of the class. So this box, now we're doing a one-dimensional problem, so we're going to treat this as a one-dimensional box, even though clearly it's not one-dimensional. So it has an inner diameter of roughly 0.4 meters. So for our example right here, we have L equals 0.40 meters. M equals, it's about half of that. So M is about 10 grams or 0.010 kilograms. So that means that the ground state energy, if N is equal to 1, is equal to pi squared h bar squared over 2ml squared. That's equal to, okay, I don't have room to even write that on the same line. H bar. You probably know H, 6.626 times 10 to the minus 34. For this class, H bar is so common that that's what it shows in the front cover of the textbook is H bar. And so H bar is 1.05457 times 10 to the minus 34 joules times seconds. Let's not forget to square both of those. Divided by 2 times 0.010 kilograms times 0.40 meters quantity squared. So when you have a calculator handy.
You better double check me. 3.43 times 10 to the negative 65.
3.43 times 10 to the minus 65. Is that right?
Yeah.
Now, just to give us a rough ballpark to see if she's right, we can do it in our heads. This is approximately 10 to the minus 34 squared, which would be 10 to the minus 68, times pi squared, which is approximately 10, so that makes it 10 to the minus 67 on top. And then the bottom is, this is 10 to the minus 2 times 1.6 times 10 to the minus 1. So if you put it all together, you have about 3.2 times 10 to the minus 2 on bottom. So we had 10 to the minus 67 over roughly 3 times 10 to the minus 2. No, it's 3 10 to the minus 3 is equal to about 3 times 10 to the, let's see, 60 minus 65. Yep. So just rounding, we can get to 10 to the minus 3 times 10 to the minus 65, which is really close to what she got. So I have full confidence. Okay, so how would we typify this? This is a high energy or low energy? It's pretty obvious, but I have to ask the question before I move on. Low. How fast is it moving? It's clearly not relativistic speed. So we can just say with this energy, if our kinetic energy, which our textbook uses T for the symbol, is equal to 1/2 mv squared, and that's equal to 3.43 times 10 to the minus 65 joules, then V is equal to the square root of 2 times 3.43 times 10 to the minus 65 joules divided by 0.010 kilograms. 6.43 times 10 to the minus 63, square root of that.
8.28 times 10 to the negative 32.
So this particle, if it's in the ground state, is moving at roughly 8 times 10 to the minus 32 meters every second. So if I wait 10 to the 32 seconds, I'll see that bad boy move 8 meters. How long is 10 to the 32 seconds? Pretty sure it's longer than the age of the universe. Well, I didn't do the calculation, but I'm pretty sure.
Yeah.
So it has an energy that's not zero, but way too small for us to discern that it's not zero. So we haven't defied quantum mechanics. We just have no way of observing the values at that level. To our eyesight, that's just at rest. I can sit here and I can watch it for years. I'll never see it move because my years are never going to come close to that number. Make sense? All right. So we now have a quantized system. So summarizing what we have now psi is equal to d sine of kx, where k is equal to n pi. We usually will come back and instead of putting kx, we'll just put n pi over L. So d is equal to sine, right, don't have to have that when I do this anymore. I need to write it so it's more legible. One more thing I need to do. Because I have multiple values of n, my psi is now psi subscript n. I have all of my different solutions. How many solutions do I have? Infinite, because n is just a positive integer. So I have an infinite number of solutions, each one with a different energy, each one with a different wave function. But I'm not done. I'm now to the part that you guys are able to handle. What's the next step in what we've done? We have a wave function. What was the next step? So you guys, Kid says you guys were joking about normalizing in his class.
Yeah.
So they're learning something.
He doesn't call it like probability density though. He calls it distribution function or something. Same thing.
It is a different thing, but it's the same idea.
Well, he was using it like we were normalizing it the exact same way.
Yeah.
Except there wasn't the complex like psi star.
We were talking about that's the probability of particle having a different speed, and so it's in a different space, if you will.
Okay.
Okay, so now we do the stuff you already know. So we need to have, I'm going to write it this way. The expectation value of 1 should equal 1. Does that make sense? Because my calculation for normalization, the integral over all space of psi star psi dx, well, I just put 1 for my operator there. Now, no one ever would say the expectation value of 1 is 1 and put 1 for the operator, but it is fundamentally what we're doing. And this is the only time I think that I'm going to be dumb enough to do this. This is the technically correct way of doing it. I have the integral in region 1 plus the integral in region 2 plus the integral in region 3. So I've integrated over all space. Now, why did I say this is the only time I think I'm going to be dumb enough to do this? Yeah, because we're integrating zeros for 2 of those integrals. What's the point of writing it out if you know it's 0? The reason I wrote it out is so you don't come back to your notes later and say, wait, why didn't we integrate over all space? Well, we did integrate over all space. It's just that it was 0 for most of it. So now we have to do that integral. Integral of d star times sine of n pi x over L times d sine of n pi x over L dx from 0 to L, which is going to be d mod squared, integral of sine squared n pi x over L dx from 0 to L. Now notice I kept n in here. We had 4 in what we did for the test. We were very specific. Here I'm going to do all of them normalized in one calculation. So of course I have to look up my integral table. And when we looked up our integral table, we found that if we set u is equal to n pi x over L, therefore du is equal to n pi dx over L. So dx is equal to L over n pi du. Then my integral becomes okay, so I'm substituting for my limit, and since u is equal to n pi x over L, I substituted L for x, and so if I put, let me change to this thing that won't stay. If I put in L for x here, the x and L cancel, and it's just going to leave n pi. So my limit for the integral is going to be n pi sine squared u du. And now we look at that integral table that I gave you on the test. I don't remember what the integral was, though.
1/2 x minus 1/4 pi minus, I don't know, something with sine.
Yeah, I know that the rest of the terms were 0, so I didn't write them down.
Yeah.
You don't have it because you gave it back to me, I think. Maybe you didn't. Maybe you
I
didn't.
don't know if I did that. Yes, minus 1/4 sine 2x.
What's the middle term?
Oh, minus 1/4 pi.
And then plus, you said 1/4.
Minus 1/4 sine 2x.
Okay, so there we're doing everything in its complete detail. So that's equal to, oh, come on. equals d mod squared L over n pi times 1/2 n pi minus pi over 4 minus 1/4 sine of 2n pi minus 1/2 0 plus pi over 4 plus 1/4 sine of 0. There I did everything in its groovy details. But sine of 2n pi is always going to be 0. And sine of 0 is 0. And minus pi over 4 plus pi over 4 is 0. And 0 is 0. So I have d mod squared L over n pi times n pi over 2 is equal to 1. And I know it's time to go. Cancel the n pi's. And I can solve this for d mod squared is equal to 2 over L. Square root both sides. And I have d is equal to plus or minus square root of 2 over L. Now, this is only the real solutions. There are imaginary solutions as well. The imaginary solutions times e to the I theta. That gives you all the solutions. But we will always have this kind of thing, and so we just ignore that.
And why does the book say that only the positive solution matters? The square root of 2 not the negative?
Well, it doesn't matter. You can use any of them. So just chose one. Chose the most convenient one. Right. We'll continue with the particle in the box next class period. You look at the lecture schedule, I think